You know, so again, we've learned a lot. We've moved past 4-1, and I'm not a real big fan of 4-1. You've heard that me probably say that last time. Listen, 4-1 taught me about critical numbers, and it makes me find critical numbers. But then it makes me do this thing. It also taught me about mins and maxes, extreme a little bit. And then but it's kind of making me work on this closed interval, which I kind of like to move past. I'd like to work on the entire number line is really where I like to work. So there's these funny questions about working on a closed interval. Now the truth is though, listen, so I'm not a big fan of those questions, but then when you put that in the context of a word problem, it makes a little more sense. And so I am kind of a fan of this one. 69 is a little word problem. There isn't, so I guess I didn't assign too many word problems, but so this is good. This is, let's see what it says. It says the formula for power output of a battery is this. So they've got a formula for power output, VI minus RI squared. Okay, power output for a battery. And then they tell me what all these letters mean, variables mean. V is the volts, the electromotive force. It's the force in volts. R is the resistance in ohms. I is the current in amperes. Find the current that corresponds to a maximum value of P in a battery for which V is 12 and R is 0.5. Now let me stop there. There's a lot of variables up here, but I think what they just told me was that they want me to maximize the power P. So that's kind of like my Y, my function that I'm trying to find a max or a min. And I think they said for which current I. So I think my I is like my variable X. So I'm trying to help you realize that this is sort of like Y, and that I is sort of like your X. And then those other variables, V and R, are given to be constants. When I just read this sentence, it said that V was 12 and R was 0.5. So here we go, I'm filling that in. So my power is, V is 12, 12I, 0.5 I squared, right. So given an R and given a V, the current I is the variable, and P is the other variable for power of this battery. And they want to know when it's a maximum, so I know how to do that. Take a derivative, set it equal to 0, look for critical numbers. Take a derivative, set it equal to 0, look for critical numbers. Right. Wait a minute. I think I'm working on a closed interval. Let me read a little further here. Hang on just a second. Yeah. Assume that a 15 amp fuse bounds the output in the interval 0 to 15. Yeah, I guess that's what a fuse does. The current I has to stay between 0 and 15. If it goes above 15, it blows the fuse. Yeah. That's kind of what happens on fuses, I guess. I mean, I'm not an electricity expert, but I have blown a fuse in more ways than one. All right. So it does look like I'm looking for I'm working on a closed interval. I'm looking for critical numbers. This is a good problem, but it was set in a word problem. Here I go. I'm looking for critical numbers. The derivative is 12. It's probably hard to stare at this and realize that I is the variable, but it's not that hard. I is the variable. The derivative is 12 minus. Well, 2 times a half is a 1. I to the, yeah, there it is. 12 minus I. You okay? Set this equal to 0 to look for critical numbers, and when does this equal 0? 12. When I is 12. Cool, so I found a critical number. My critical number lives in my interval 0 to 15. So that it's a legitimate critical number to look at. They want to know when I have a maximum power. If you remember what we learned in this section is the maximum could occur at that critical number, but it could also occur at the endpoints of this interval. So what I should do now is go to my power function, go back to the original function, and just check. What's the power when the current is 0? What's the power when the current is 12? That's my critical number. And what's the power when my current is 15, right? I should check my endpoints, and I should check my critical number, and just see who's the biggest and who's the smallest. That's finding maxes and mins on a closed interval. But we're in the context of a word problem. So this is fun. Here we go. The critical number was easy. Here we go. I'm plugging in a 0 for the I, and I get a power output of 0. I guess when you have no current, you got no power. When you plug in a 12, you get 72, I think, is your power output. When you plug in a 15, you get... what'd you say? Thank you. 67.5. Cool. So our maximum power output comes at a current of 12 amperes, I guess. I don't know. I guess I'm done, right? Did I answer the question? Maybe. Hang on. Find the current that makes me have a maximum value of P. Okay, we did good. Now there is one question at the end. Could this change if the 15 amp fuse was changed to a 20 amp fuse? So in other words, if I don't have a 15 amp fuse and I have a 20 amp fuse, then this could go as high as 20. Would that make me have more power? Let's check 20. In other words, let's check 20. You guys with me? In other words, changing the interval. Let's check it now. Plugging in a 20. That's a 40? Is that what you just said?
Yeah.
So, no, it doesn't change. No, the maximum still occurs at 12. The maximum power output still occurs when I is 12. So, I don't know. The math wasn't hard. Reading all those words might have been kind of hard because it's words and science and physics and electricity. But I don't know, that was good though. That's worth doing. I appreciate that. I mean, that's why I assigned it. Again, not a real big fan of working on a closed interval, but in real life, sometimes you are working on a closed interval. We'll see that a little more here when I move into 4-7. When I move into 4-7, there might be some restrictions. I might be working on a closed interval. So there is some value to that. Any other good questions? Anywhere, anytime. I'll take any questions. 4.625. Now wait a minute. Wait a minute. No, I'm kidding. Till I look at this thing. Ooh, that's a damn good question. 4.6, number 25 is a function. It is 10 over 1 plus 4 e to the negative t. 10 over 1 plus 4 e to the negative t. This is a cool function. I recognize this equation. I know about this guy a little bit. Be glad to share my knowledge with you. What are my directions? My directions are, holy shit, my directions are do everything, right? I mean, analyze and sketch the graph of the function, label the intercepts. I'm not a big fan of the intercepts. The extrema, that's the mins and maxes, the points of inflections, the asymptotes. Yeah, do everything we've learned this chapter. So, and half hour later, maybe we get the answer. These are long, tough problems. That's why you should do a few, but don't do hundreds of these. You know, in order to analyze the heck out of this, the hard part maybe is sort of, I need a couple derivatives, right? I need a couple derivatives. And you probably haven't done a derivative like this maybe in a while. I'm going to help you. In order to do this derivative You might say quotient rule, but because there's no variable in the numerator, I really don't have to do a quotient rule. One thing I could do, I could rewrite this like this. I mean, this whole denominator can be moved up and called to the negative 1. I mean, you know that, I hope, algebraically, you know that. And now, I'll do a derivative now. The derivative is, now it's just a power rule, chain rule thing, you know. Negative 1, which is negative 10, and then all this is to the power of negative 2. That's how you do a derivative, right? And now, the chain rule says I have to multiply by the derivative inside. The derivative inside is the derivative of the 1, which is nothing. And then the derivative of a 4e to the negative t is actually just a 4e to the negative t. But then you have to multiply by the derivative of the little negative t, which spits out a little negative 1. Did you follow that? That was chain rule. That was chain rule city. Welcome to chain rule city. There's power rule, the derivative inside, and then that little baby derivative at the end. All right, let me clean this up and see what this looks like. This is my derivative. I'm going to drop in back to the denominator and call that 1 plus 4e to the negative t squared in the denominator. And so then what's left in my numerator? A positive, it is a positive 40e to the negative t. You guys okay? That's calculus. It's a derivative, and it's cleaning up a derivative, and that's a derivative. You have questions about my little cleanup there, my little work there? Okay, so now I'm looking for critical numbers. And so to look for critical numbers, I need to ask myself two questions always. When is this derivative 0? And or when is this derivative undefined? So when is this derivative 0 means when the numerator is 0. And so I could just set the numerator equal to 0, and I can do the steps, I can do the algebraic steps, but I don't, because I know an e function never equals 0. So there's no solution to this. If you did the steps, you'd find that out. I mean, watch what happens. The steps are maybe divide by 40, right? So then you have this e function equals 0. You might try to take the log of both sides. And that's when you'd realize the log of 0 is undefined. You can't do the log of 0. The calculator would tell you that, actually. It would say error. So anyway, there's no solution to this. An e function never equals 0. So it never equals 0. So far, there's no critical numbers. Hey, maybe when the denominator equals 0. When does this denominator equal 0? And if you move the 1 over and divide by 4, you get this e function equals a negative 1/4. You try to take the log of both sides, and you can't take the log of a negative number. You cannot take the log of a negative number either, or 0. So there's no answer to this either. So there's no critical numbers. There is no critical numbers. Critical numbers. None. That's kind of interesting. If there's no critical numbers, can you do a first derivative test? Who do you put on here? Nobody. And so you don't have, there's no critical numbers. I guess there's no maxes, there's no mins. Why am I even doing this? What will this tell me? There's no maxes or mins. What would it tell me if I did a test here? Bless you. It would tell me increasing and decreasing. Maybe I shouldn't check it out. Now listen, you know, when you put a critical number on there, that divides it into these different regions. How many regions do I have? I got one big region. I can pick any damn number I want. I'm going to pick a 0. It's a test number. It's not a critical number. I'm plugging it. Where am I plugging that? Into the derivative to see if it's positive or negative. Okay, here I go. When you plug in a 0, that's positive 40. When you plug in a 0, that's positive. When you square it, it's positive. It's positive. So what do you know about this function?
It's increasing.
It's always increasing. Yep. And it ain't got no max or min. And it's always increasing. You want to do a second derivative? This is where, now see, this is where I would like to cheat. I would like my solutions manual so I can look it up. Because this is hard. I want to do a second derivative. I think there is an inflection point here. I want to do a second derivative, but it's difficult, I think. You ready? What would you do? I guess I'd do a quotient rule. I mean, I could try to get fancy, but I'm just going to do a quotient rule now. See, a few minutes ago, I didn't have a variable in my numerator. So with no variable in the numerator, I could move the denominator. It really wasn't a quotient rule or a product rule. It was just a chain. It was just a power rule. But now I got the variables there. The variables are there. I think I better do a quotient rule. You ready? Derivative of the top.
-4e to the -2.
I like that. Now, do you guys like that?
Mm-hmm.
The derivative of the top. It's really just himself.
Mm-hmm.
Except but the chain rule spits out a little -1. Okay, right down the bottom. Great, right down the bottom. Minus, right down the top. And take the derivative of the bottom. The derivative of the bottom. I think I should bring a 2 down. Let me do a little better job here. I'm bringing a 2 down. And then I got 1 plus 4 e to the -t to the first. That's how you do it. Then you got to do the derivative inside. What is the derivative inside there?
-4e to the -2.
A -4 e to the -t. She's right. All over. That denominator squared. Oh my God. So that's that denominator to the 4th.
Yeah.
Boy, I'm glad I didn't assign 12 of these problems. There's one of these, right?
Yeah.
There's only one of these.
Yeah.
Yeah, that's good stuff, you guys. Hey, I'm going to cancel one of those. There's a 1 plus 4 e to the -t right there. There's another one there, and there's another one there. You can. Here's your big minus sign right here. So I'm going to cancel one of these here. I'm going to cancel one of these here, and I'm going to cancel one of these here. You follow that?
Wow.
That's algebra. It's kind of like I factored one out front and then I canceled it, but I prefer just to cancel it while it's sitting there. It's a little less writing. What do I got left now? Jesus. I got one of these left right here. Maybe I should distribute this. Good God. -40 e to the -t plus -160 e to the -2t. I'm multiplying, you guys. I'm multiplying this times the 1, this times this. When you multiply those e's, you add exponents, e to the -2t. All right, what am I doing over here? This is gone. There's a negative sign. There's a -80. Here comes a -4, so that's a positive 320. And there's an e to the -t and another e to the -t. That, when you multiply those, that's e to the -2t. This is tough, you guys. I'm sorry. This is tough. I mean, I'm not really sorry. Whatever. I'm combining these two like terms here. I'm combining those. That's going to be a positive 160 e to the -2t all over this denominator cube. This is the second derivative. Pretty cleaned up. That was tough.
How'd you get the cube on the bottom?
I canceled one of those quantities. There was 2 of them there. There was 4 of them there. There was 1 of them there. I canceled one. He's gone, 1's gone, and 1's gone. Now what? Oh, I'm looking for inflection points. Jeez. Gotta remember what the hell you're doing. Looking for inflection points.
So the
When does it equal 0? I could say when does it undefined, but we already looked at this denominator. This denominator never equals 0. So it's really about when does this equal 0? which is really about the numerator equaling 0. You know, I think I'll factor. What the hell am I going to do there? I think I'm going to factor out a negative 40 e to the negative 2t. I think I always factor out the lowest power, if you remember.
Right.
That's my strategy. So, geez, what the hell am I left with then? Now I'm confused. If I factor a negative 40 e to the negative 2t out of an e to the negative t, am I left with an e to the t?
Yeah.
Because if you multiply it back, you would, yeah. All right, what about over here? You factored out your e to the negative 2t, you factor out a negative 40, so I think you're left with negative 4. Dude, this ain't bad. That's my, sorry, I'm setting my numerator equal to 0. This is my numerator. I factored it, it's equal to 0. When does this equal 0? Never. When does this equal 0? I'm finally going to get it. When does e to the t minus 4 equal 0? Move the 4 over, take the log of both sides, and the answer is the natural log of 4. Move the 4 over, take the log of both sides, natural log of both sides. We found it. A PIP. What's a PIP? Potential, yeah, I called it possible. Possible or potential. Inflection point, yeah. That's what he is. We're not sure if he's an inflection point unless it changes concavity. I guess I should put him on a number line and test the concavity. Good God. Tell me, where is log 4? I don't even know how to put him on a number line. Where is log 4?
1.386.
Okay, 1.386. What did you guys say?
Yeah, 1.3.
1.39. Okay, thank you. All right, so now I got a test around him. All right, now I'm starting to get aggravated. Pick something over here. I'm going to pick a 0. And what do I do with that 0? Plug it into, no, the second derivative to test the concavity. God dang it, there's my second derivative. All right, here we go. If I plug a 0 in here, I'm pretty sure that denominator is positive. If I plug a 0 in here, this is e to the 0. This is easy. That's a 1. That's a 1. That's negative 40 plus 100. That's positive. I think it's positive. And therefore, I think it's concave up. What about to the right? I guess I could pick a 2. This is not going to be as fun. When you pick a 2 and plug it in, you're going to get some nasty little numbers here. E to the negative 2, but it's positive. And it's multiplied by 4, and then you add 1, and then you cube it. The denominator is positive again. What happens when you plug a 2 in here? E to the negative 2, negative 40, e to the negative 2, and then 160 e to the negative 4. Dude, I don't know. I need help with that. I need help. I got to figure out. I'm plugging a 2 in. Is negative 40 e to the negative 2 plus 160 e to the negative 4. Is that positive or negative? I don't know. I need to know. You think it's negative? He says it's negative. Good, thank you guys. So it's negative. And if it's negative over positive, it's negative. Which means it did change concavity, which means this is an official inflection point. Good God, that was a hard problem. I mean, how hard was it? Those derivatives were hard, right? The derivatives were kind of hard. Derivatives were kind of hard. Maybe not the first one. The second one can be tough. So maybe I should graph this now that I know what's going on. the truth is, to me, this is a famous graph. I know about this graph. I told you that when I started. Just for fun here, plug in a 0, please. I want to plug in a 0 for t. I want to plug in a 0 for t. Plug in a 0 for t. That's e to the 0, which is 1. So that's 4 plus 1 is a 5. What's 10 divided by 5? 2. So when you plug in a 0, you're at 2. So that, now, watch this. Can you do this? Can you take the limit as t goes to infinity? Well, when t goes to infinity, let's see. When t goes to infinity, what's e to the negative infinity? Do you know? You could type in e to the negative 1,000 on your calculator. That would help. What is e to the negative infinity? You can think of an e function in your head. You can think of an e function in your head. Look at this. Here's an e function. What's e to the negative infinity? 0. Yeah. There's a lot of ways to think. But I'm asking to do the limit as t goes to infinity, and this goes to 0. This goes to 0. So what's the answer? 10 over 1, or 10. Listen, as we go out to infinity, the y value approaches 10. It turns out there's a horizontal asymptote at 10. This is a famous function. It's called a logistic function. There is no, I'll put that word here. It's called logistic. There's no min or max, but it does this beautiful shape here. Watch this. It does this. It increases. There's no min or max. It increases forever, right? Is that what we said? But there is a place where it changes concavity. It goes from concave up, and then somewhere it switches to concave down. Did you see that? Look at that picture. This is a classic logistic picture. It looks like this. See that? There's no max or min, but there's an inflection point. There it is there, specifically. There it is there, generically. And I'm sorry, I'm a little out of scale here, but I'm calling that my inflection point. 1.39, is that what we said? It's concave up, it hits that inflection point, and it's concave down. It's increasing forever, but it does have this asymptote that you might not have thought about. I just happen to know these guys have this asymptote here. This led me to the idea of the asymptote, the horizontal asymptote. This is famous in populations. You know, sometimes you might have done some population growth problems, and a lot of examples, they just say populations go crazy. They just grow. And in a lot of examples, that's what they do. The human population is just exponentially increasing. Certain populations are exponentially increasing. But some populations are limited by their environment. So usually what happens in some populations is this is population growth, but it can't grow forever. The rate of growth begins to slow down. The rate of growth begins to slow down. You hear that? And we are limited by our environment. Like if we're in a little pond, there's only 10 frogs can live in this pond. We're limited by our environment. So anyway, it's a math problem. I'm trying to say it pops up in real life studies, science and math and biology. It's a logistic equation, and it has its uses. But it's tough to do all that derivative work. It's tough, just kind of tough to do that second derivative, that's all. What else, you guys? Any other good ones? Now you're scared to ask me any questions after that. Well, let's do this 4.7. So I'll introduce it and we'll spend a couple days on it. And then there's a few other minor things before this chapter is over next week. So we're doing a quiz Friday and then a test next Friday. So we got a few things to discuss before next Friday. Yeah?
What chapters does the quiz go?
Okay, we talked about that earlier.
I think we did.
Yeah, it's all this stuff.
All right.
Right, up to today. I need to talk about 4.7. And you can start working in 4.7,
So that won't be on the quiz.
but it ain't on the quiz.
Okay. That's
But that doesn't mean you can't work on it. Do it.
right.
Right. What is 4.7? It's word problems, dude. It's max, min word problems. We've been looking for maxes and mins on these things. That's what we're doing. But now let's put it in the context of a word problem. They're called optimization problems. If we're trying to optimize, I think we're trying to maximize or minimize something. Optimization. You know, in business, we try to maximize our profits. We try to minimize our costs. Whatever. Here's one. I'm making this one up. A farmer has 1,200 feet of fence. He wants to build a rectangular pen for his. He wants to build a rectangular pen. He wants to build a rectangular pen. You didn't know farmers needed calculus, did you? Rectangular pen for his goats. Also, farmers don't know how to punctuate. They put periods right in the middle of sentences. Farmers are a trip. They need calculus, though. Here we go. He's trying to build a pen for his goats. What's he doing? Oh. I might describe this pen, but instead of describing it, it's kind of easier to tell you that he needs a couple of cross fences. So it's a rectangular pen, but he's going to put 3 cross fences across there. Of course, there's also 2 end fences, but he's putting 3 cross fences because he has the mamas, the babies, and the daddies, and
Misfits.
the newborns. Yeah, he has them all separated. I don't know why. Society, we should learn to get along. But anyway, he's got these things all separated. What's the deal? Oh, here's the question. What are the dimensions? What are the dimensions for maximum area? So in other words, should he build a 10 by 20 pen, or should he build a 15 by 30 pen, or what are the dimensions that maximize the area? Have you ever seen a question like this before? This is a famous question. Yeah. In fact, I do this. We do this in college algebra sometimes. We do it in college algebra. And in college algebra, the idea, you don't know calculus in college algebra, but what you form here by doing, you have to do some work here, but what you form is a quadratic equation, which is a parabola. And if you're looking for when it's a maximum, you find the vertex in college algebra. In this class, if you're looking for when it's a maximum, what do you do? In college algebra, you find the vertex. In calculus, you take the derivative and set it equal to 0. That'll be the vertex. Yeah. Right. But the build up to it is kind of what's hard for students. But you guys, if you've seen it before and done it before, and you're probably better at this than my college algebra students. You have to create an area equation. Look, you have to think about this. I'm trying to maximize area. So area is the thing I'm trying to take the derivative of. And so what I would do is I would label the width of this thing X, and that way label the length Y maybe, or L for whatever. And so what would be the area of the entire pen? I know I got it divided into a bunch of little mini pens, but what's the area of the entire pen? X times Y. Cool, dude. I want to take the derivative, set it equal to 0, blah, 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 blah. But wait a minute. You don't take a derivative of A with variables X and Y. There's too many variables. I want to get rid of Y. I want to just have X's or just have Y's. I got too many variables. My area Yeah, I need one variable, right? I mean, so I need x or y. So wait a minute. So that's what I want to maximize. This is who I want to take the derivative of. But wait a minute. There should be another statement I can make, a certain condition that has to be met. And that is the fact that I have only 1,200 feet of fence. Thank you. So this is another equation. And what can I say? You know, sometimes you interpret that 1,200 as being the perimeter. It is the perimeter, except I do have these cross fences that need to get added into the perimeter. So I would say that I have this x, this x, this x, this x, and this x. They're all the same because it's a rectangle. This is a y, this is a y, and I think I could say that all that adds up to 1,200.
Right.
So 2y plus 5x has to be 1,200. And I'm going to pause right here. You guys probably know what to do and everything, but let's just listen to me a second. It's very typical for these problems to have this sort of strategy, which is one equation you're going to do the derivative of, but it has too damn many variables. Another equation that's sort of a condition that has to be met, like we have 1,200 feet of fence. So it's like we're trying to maximize area subject to this condition. And so there's usually kind of two equations. I think your book sort of calls it a primary and a secondary equation. I don't really need those words, but one of them you're doing the derivative of, you're trying to maximize. The other one is sort of there, let me just say this, to help you get rid of one of those variables. I mean, what I want to do is use this to get rid of y. I want to solve for y. I want to move the 5x over. 2y equals 1,200 minus 5x. I want to divide by 2. So y equals 600 minus 2.5x, if you don't mind. You following me? I use this to substitute into here. So my area equation becomes 600 minus 2.5x. How are you guys doing? This is the excitement. We're about done. I would distribute it and sort of clean it up before I did the derivative. I would. I get this. And then my college algebra students would go find the vertex right now of this parabola. But you're not going to do that. You're going to take the derivative and set it equal to 0. Which, by the way, it's finding the vertex. But you're going to take the derivative. 600 minus 5x. You're going to set it equal to 0. And this will be the x that gives you a maximum. When your derivative is 0, this is the critical number that gives you a maximum. I'm sure it is. Move the 5x over. Divide, and x is 120 feet. Hey, you know, all I really found so far was a critical number, right? When the derivative equals 0, it's a critical number. I don't really know if it's a max or a min. And if I had 2 or 3 or 4 critical numbers, then I guess I better go test and figure out who's the max and who's the min, you know. But the truth is, on these word problems, what tends to happen is they ask for a maximum, you do the work, you only get one damn critical number, and it's the answer. I mean, you don't even have to stop and prove to me that it's a max. It is the max. Now, if you had 2 critical numbers, then you might want to check which one's the max. But they're looking for a maximum. We found one critical number. This is it. This is the critical number that gives me a max. The question actually asked for dimensions. And so I think when they said dimensions, they meant like, you know, the length and the width of this thing. So far what we got is 120 feet by, I don't know what y is. Can I find y? Oh, I got x. I can plug it right here and get y. So y is 600 minus 2.5 times that x. So that's 300, huh? Okay, these are the dimensions that maximize the goat pen. And that's, I don't know, that's not that hard of a problem. But it is one of our typical, it's a typical word problem in that you kind of got these two equations. One of them you're maximizing, one of them that's got a condition that's got to be met. And you learn how to use these two equations to take the derivative of this one, find your critical number, and you got it. The question could have said, what did mine say? What are the dimensions for maximum area? Okay, so I answered it. They also could have said, what is the maximum area? Well, I still would have done all this to tell you the truth, and then at the end, I guess the maximum area is well, what's area? X times Y, length times width. I mean, right, so at the end, my area is 120 times 300. 36,000 square feet. I like to throw, go ahead.
I was just going to say, or ask, is that what each of the little boxes contain, or is it the whole thing?
Okay, what do you think? So I found X. So X is 120. And then I plugged it in and found Y. Y was 300. When I plugged that X in there, Y was 300. And look, what's Y? Look at Y.
There's for the whole thing.
That's Y. That's X. So we just found the area of the whole thing. We found the dimensions of the whole thing. When I set it up, I looked at this thing and I said, the area is X times Y. So I set it up to do the whole thing.
Right.
You know, some people like to, I mean, I think it complicates things. If you call this little section Y, then how many damn Y? Now you got 1, 2, 3, 4, 5, 6, 7, and you got 8 little Y's. And your little Y would just be this Y for this pen. And anyway, then you'd be maximizing the area of this pen, which would be okay, but we really I wanted the whole pen.
But I don't understand how that works then if you have, oh, okay, never mind, because we included 5x in the equation.
Yes, we did.
Okay, so that's why you're
That's my fences. That was part of my 1,200 foot of fence. Had to have those guys. Yes, it had to have 2 of those guys. It had to have 5 of those guys for my 1,200 feet of fence. You're right. You know, I like to do these problems like this, and I like to do them with a cross fence in there because it makes it more interesting. You know, the typical question is, you know, you just build a pen with no cross fences. So a rectangular pen with no cross fences. The problem with that is you could go through the math and go through the calculus, but I know the answer. What rectangular pen, forget the cross fences, just a rectangular pen, which shape would give you the most area? A square. So then if you know it's a square and it's 1,200 feet, the answer is 300 by 300 by 300 by, I divided by 4, it's 300 by 300.
Yeah.
You with me? If someone says, I want to build a rectangular pen and get the maximum area, and if there's no other interesting parts of the problem, it's a damn square. So it's too easy. So you got to throw some cross fences in there. Watch this. Put a little, I threw 3 cross fences in. How about put a little 15-foot gate right here, baby. Maybe a little 4-foot gate over here for the people to walk through. Maybe, oh shit, maybe you got to double fence it right here, triple fence it, because that's where the big mean goat lives. So you got to double up your fence. But anyway, you can make it real complicated. I don't make it too complicated, actually. I just put cross fences. Hey, what if it didn't have to be a rectangle or a square? What would be the best shape for the most area? A circle.
A
Yeah.
circle.
Yeah. I mean, if he really wants the most area out of his 1,200 feet of fence, he should build a circle. But have you ever built a fence that's a circle? It's not that easy.
Yeah.
I mean, you gotta get the boards to bend, whatever. It's easier to mow, though. This is a pain in the ass to mow this. You know, how do you...
No, you won't have to mow it if you've got goats.
Well, that's true. That's true. But I was thinking, when you mow this, you know, you always leave these corners, you know? But this would be cool to mow, dude. You just mow right here. Get some spiral action going here. You ever flown in an airplane? Has anybody flown in an airplane? I mean, nowadays you should have. Maybe, maybe not. But anyway, when you fly across the country, you know, and you look down across they have all these circles, you know, these. But they're growing stuff, and I think what they got some kind of irrigation system that runs around in a circle.
They drill a well in the middle and it just swings around.
Is that what they do? They drill a well in the middle.
They drill a well in the middle.
Right, and then this thing kind of is on wheels, and it goes around. Right, you got all these.
They do that here.
Yeah.
Or do half.
Well, you see it better when you're up in the airplane. You see these circles. Let's do another one. Let's do another one. That was mine. I made that up. But what I'm also trying to teach, besides farmers and goats and is the problem-solving strategy of this type of problem, which is sort of these two equations that you work with. Let's just, actually, there's a couple exceptions to that. You don't always have two equations. There's some different ones. Let me see. A lot of them are about maximum area. Hey, what time is it?
What time?
8:57. Okay.
9:15.
Thank you. All right, let's do one more here. Let's do one more. Man, I didn't assign too many good ones in here. Look at this funny problem. Okay, here's one I found in the book. Number 6. And you know, this is not, it's called a word problem, but there's not too many words. It's about numbers. So their question is, find two numbers. I mean, it's not about notes and industry or profit or, you know, it's not much of a word problem. It's just about numbers. They say, find two numbers. Here's what has to happen. The second number is the reciprocal of the first number, and their sum is a minimum. All right, hold on. They just said that there's, okay, two numbers. Can I call them X and Y? Okay. They said their sum is a minimum. So the sum of two numbers, I'm going to call S. And what would be the sum of X and Y?
X plus 1.
Thank you. Good job. And this is the guy I'm trying to minimize. So I'm getting organized here. See, I get organized. So they want me to minimize this sum, but they must have told me some other requirement or some other condition. Kind of like the last one had the 1,200 feet of fence. That was a condition. This had to have some condition, and the condition is that one of the numbers is the reciprocal of the other one. You know how to write that? What does that mean? One of the numbers is the reciprocal of the other one. Yeah, that's what they said. Okay, so now I think I'll go replace this. I'm going to replace this y with a 1 over x. So that's, you know, so I get one variable over there. And now I can take his derivative. And it shouldn't be too bad. The derivative of an x. And the derivative of him. No. This is a power rule. You got to move it up and do a power rule. You might have forgot. So it's x to the negative 1, but when you do a power rule, it's negative 1, x to the negative 2. You guys following me?
It's negative 1 over x squared.
Move it up. You do a power rule, so it's negative 1, x to the negative 2. It's negative 1 over x squared. You set it equal to 0 because you're looking for the critical number. After you take a derivative, you set it equal to 0. And this one's going to be easy. I think it's going to be a 1, right? Yeah. Because you move, let's see, if I move this to the other side, if I do the algebra, I'll multiply this up here. I'll get this. I'll take the square root of both sides. And technically it equals plus or minus 1, but I think if I read the directions, they wanted positive numbers. Find two positive numbers. Yeah, that's what they said. So it won't be the negative 1. It'll just be the positive 1. And what's the reciprocal of positive 1? 1. I mean, my two numbers are 1 and 1. Yeah, right. We could have guessed this. Some of these are kind of funny. I mean, hang on just a second. Two numbers that are reciprocals to each other and their sum is a minimum. Right? So we're done. We found it. The critical number we got was 1. And so the y value is 1. So those are my two numbers. And by the way, what is their sum? If those are the two numbers, what's the sum? 2. So apparently that's the minimum sum. I mean, I just want to play around here a second. Watch. What if one of my numbers was a half? What would be his reciprocal?
2.
Okay. What would be their sum? What would be their sum? 2.5. Okay, well, so far he is the minimum, right?
Right.
I mean, what if one of them was 1/3 and the other one was 3? What would be their sum? Okay, yeah, I'm not going in the right direction here. I'm looking for somebody else that could be a minimum, and I won't find one. Our calculus proved to us that this is the minimum. I'm just playing though here. Let me keep playing a second. What if one of them was 4/5 and the other one was 5/4? That might be, hang on now. What's that sum? Oh shit, what is that sum? 20ths, 16 20ths, and 25, 41 20ths, I think. Hey, 41 20ths is 2 and 1/20. Damn, he still wins.
Yeah.
I mean, I'm not disappointed. It's supposed to win. So there's a lot of numbers that are reciprocals to each other. But this is the one where the sum is the minimum, right? Okay, like I said, there's a few more interesting problems than that. I guess you should do the ones I assigned. I didn't assign that many in 4-7. But I'll quit today, and I'll see you 8 o'clock Friday. Oh, I wanted to make one announcement. Here, let me hit pause here, or off here.